In this video, we are going to take some of the things we've learned about how light behaves as it moves into and out of different media and put that to some good practical use. So what I've drawn here, this sort of oblong shape, we normally would call a lens. This is just one kind of a lens. There are other kinds of lenses, but we probably recognize this as looking like a magnifying glass, right? So this would be made of glass or crystal or maybe clear lucite, something that is going to bend light as it goes into it. Now, we know how to handle what happens inside this. We've seen the law of refraction or Snell's law, whatever you want to call it. We know that the light will bend at this interface. It will bend towards the normal. If it's coming from air into glass, it will bend towards the normal. And then as it leaves to go back into air, it's going to bend away from the normal. That will happen at each of these interfaces. But chances are, if I'm using a lens, what I really am interested in is what's happening outside the lens. I'm curious what this light does, what this light looks like after it passes through the lens. And so if that's the case, then I can make simple approximations and not have to do all the individual analyses at each interface, which of course you can do. But the approximation I'm making here is that the light comes in, it gets bent a few times, and it comes out looking like this. So what I've done is drawn this line straight to the center of the lens and then let it make a hard right turn somewhere in the middle. That's absolutely not what the light really does. But that's the approximation I'm making. When I draw that, and when you draw that, what you're saying is I'm not worried about the law of refraction. I'm just worried about the fact that it does refract. And if I look at the behavior over here, the behavior over here, I can do some things. All right, so with that in place, let's look at what happens. I've drawn some light rays incident upon this lens parallel to each other. They are in line with this orange dotted line, which represents the horizontal axis of this lens. And what you'll notice is as these rays come in, they are bent in such a way that they all converge to a point. Now, of course, I'm assuming my lens is ground really nicely. We take glass and we grind it into these shapes. But if it's not shaped really nicely, they won't converge to a point. But in general, you can absolutely make a lens of this shape, which will take these rays to this point of convergence. Now, we call that a word that's probably familiar. We call that the focal point. And when I do that, I can now measure the distance between the center point of the lens and that focal point. And I call that F the focal length. It is a length that'll be given in units of meters, or most likely centimeters or millimeters. But it's just a physical length from the center of that lens to the focal point over here. All right. Now, because these rays are converging on a specific point, we call this type of lens a converging lens. And just by me saying that and writing it down, you can probably imagine that later we're going to look at a diverging lens. But this is a lens which tends to converge light that enters into it, at least light that enters it parallel, to a specific point. Okay, let's run this experiment backwards. Notice I've let light be incident from the left and focused to the right, but there's no reason I couldn't take whatever's producing this light, move it around to the other side, and run it backwards. It might look something like this, right? If I just flip it over. Because I've drawn the lens nice and symmetrically, what that means is that there will be another focal point over here. I'll put it there. And I might not have drawn that particularly well, but the idea is this is also the same focal length if the lens is truly symmetrical. Of course, you can grind the lens however you want to, and in real life they do. But for this lens, I'm going to say that there's a focal point here and a focal point here that are the same distance, the same focal length away from this lens. All right, so with that said, now that we've figured out what the focal point and the focal length is, let's see what we can do with this. So, drawn another one here. Now, we normally don't use lenses to handle parallel rays, although If you had a misspent youth like myself, maybe you did. If any of you have ever started a fire with a magnifying glass, this is actually what you're doing. The sun is so far away that basically all the rays that get to any particular area on the earth are parallel to each other. And what does a magnifying glass do? It takes all of those rays and it focuses them down to a point. So it takes all the energy that's incident upon this surface and it focuses it to a point which gets really hot and starts a fire. So that's, some of you might have seen this in action. Now, what we're going to do here is handle rays that are not parallel to each other. But I've said that this is kind of like a magnifying glass. What do we do with magnifying glasses? Well, we look at things, right? We use them to investigate some aspect of nature around us. In other words, we use them to see images of objects. We would say in real life, we see the object, right? But what we're actually doing is seeing images of objects. And so let's see how that works. To do this, I'm going to put an object somewhere over here and let light come from that object and pass through the lens. Now, when I say come from the object, of course, what's actually happening is there's a light source somewhere. The light is bouncing off of that object and it gets to our eyes eventually, and that's how we see. I'm going to pick off one point on this object. My object usually is just going to look like a little arrow. I'm going to pick off one point on this object and investigate a couple of light rays that are bouncing off that point. This is not an exhaustive list of light rays, right? There are lots of light rays bouncing off this whatever point I choose. I'm going to pick out some interesting ones. I'm going to pick out the tip of the arrow and some light rays that are bouncing off of the arrow. And I'm not going to care about how they're coming in. I'm just going to care about how they're leaving. Specifically, I'm going to pick out a light ray that is propagating out from the arrow like this. That is parallel to this axis. Now, just from up here, I know what's going to happen to this light ray. It is going to be refracted such that it passes through the focal point. That's how I got to the focal point in the first place. I'm going to have to turn my paper a lot to do this. But that's what that light ray is going to do. It enters the lens, it's bent, it passes through the focal point, and carries on its merry way. Okay, fair enough. Well, what happens to light that enters the lens through this focal point? Right, so there's a ray that's propagating through this focal point. I'm going to move this focal point over a little bit. I've drawn it a little close, so I'm going to move it there, just for the good graphics. So let me see what happens here. So light's going to pass through the focal point and enter the lens here. Now, we actually already know what's going to happen here, because what happened over here when I flipped this around? Light that, if I look at it from this side, the light that's passing to the focal point here came from a parallel ray that is parallel to the axis. So that's going to be what happens here. This thing will actually leave the lens parallel to its axis. And it looks like I didn't draw this long enough. You can see what's happening. These two rays that are emanating from the same point on this object are actually converging over here. Not at the focal point. That happens to parallel rays. But these two rays are converging over here somewhere. Okay, so that's two rays I can draw. There's another one. So I would say that drawing these two rays follows two rules for what we call ray tracing. And that's what we're doing. We're tracing the path of the rays. If you're in my class, the ray tracing rules are in your canvas. If they're not, here's the first one. A ray that enters a lens, a converging lens, parallel to its horizontal axis, exits through the focal point. A ray that enters a lens through its focal point on the same side as the object exits the lens parallel. There's one more. A ray that passes through the center of the lens, that's this point right there, travels straight as if nothing happened. Let's see how well I've done my drawing. Sorry. Oh, that's not terrible. That's not terrible at all. All right. Actually getting these things to converge when you're drawing freehand with a Sharpie is, well, sketchy, if you'll forgive the pun. It was intended. But, so, I have three rays now, which I can trace, and they all converge at the same point. In general, I don't need all 3 rays to see where they converge. I can get by with just 2 of them. I'm going to show you all 3 just in case you can use them. But now what does this do for me? Well, if these rays are converging here, they're emanating from the tip of my object, they're converging here. What happens is an image of the object appears at their point of conversion. Now the object here is an arrow, but specifically these rays come from the tip of the arrow. So what happens is the tip of the arrow is here, and just to give you the punchline, the image appears thusly. You could, to find out that the bottom of the arrow is here, you can actually do the same ray tracing. If I trace a ray from the bottom of the arrow through the center point of the lens, that just looks like the straight line gets to this point. I don't even need to draw anything else converging to tell you that if the bottom of the arrow is going to appear, it's going to have to appear along that line, because the ray that comes in this way just keeps on traveling straight. So hopefully it's not too hard to see that I get an image appearing here from the converging lens. So the image is inverted and in general will be magnified. Now the way I've drawn it, it doesn't necessarily look like it's a different size in this arrow. That's a product of poor graphic skills, not of actual physics. Because in general, we know what magnifying glasses do. The size of this image will be different than the object. So we can talk about its magnification, we can talk about its orientation, whether or not it's upright or inverted. Okay, so if we can see our way through this ray tracing, let's now put some mathematics to it. I will move this up so that you can still see it. And put another sheet here. Let's put some mathematics to it. Let me introduce you to what's called usually the thin lens equation. It says this: 1 over distance to the object plus 1 over distance to the image is equal to 1 over the focal length. So we've seen the focal length, we know what that is. We've got to figure out what distance to the object, distance to the image are. That's probably not too hard to come up with. Let me get a different color. The distance to the object is the distance from the center point of the lens, same place we measured the focal length from, to the object, the placement of the object. That is, DO. Alright, you can probably see where I'm going. Distance to the image is that. It's the distance from that center point of the lens to the position at which the image appears. And of course, we already know this one, that's the focal length. So this equation relates those relative positions. 1 over distance to the object plus 1 over distance to the image equals 1 over the focal length. I'm not going to leave it in this form. It's perfectly fine to start with the equation in this form. Let me show you how to manipulate it into something a little bit more useful. Let's first of all, usually what these problems will come up as you're given some distance to the object, you're given some focal length, and you need to come up with a distance to the image. So let's just go ahead and solve this equation for distance to the image. First step, get that term on the same side, 1 over f minus 1 over d to the object. Now I'm going to need to invert my left-hand side to get the distance to the image. I can't just invert the right-hand side in this form. Let me get a common denominator by multiplying by the clever one, f over f and do over do, right? I just multiply both terms by 1, so I'm not changing anything. But I get in the denominator, I get an f times a do or a do times an f, which is the same thing because mathematics is commutative. So I can then put the numerator over a single denominator. So I get that 1 over d sub I is equal to do minus f over, I'll write it like this, f do. You can write dof if you want to, no big deal. Now I have a single ratio on either side. I can invert this equation. So if I do that, I get di is equal to f do over do minus f. And this is probably the most useful form of this equation if you're going to memorize an equation, which you don't have to do. at least not for my course. This would be the version of this to memorize, because this is what you will use most often. It comes directly from here. This is the thin lens equation, but if you solve this for the distance to the image, this is what you get. Of course, if you need something else, you should not use this form. If you need the distance to the object or the focal length, don't use this. But this is usually the most useful form of that equation. So this equation relates these quantities here. There's another equation we need to use, the magnification equation. Magnification just indicates that there's a change in size between the object and the image. It doesn't necessarily mean that the image is bigger. That's how we use this in normal life. But in this class, we will use it just to mean a change in size. It could be bigger, it could be smaller. It's defined thusly: equal to minus, that's part of the definition, don't forget that, d to the image over d to the object. What does the negative sign mean? The negative sign tells you that, or if you find that a magnification is negative, the negative sign tells you that the image is inverted with respect to the object. So you're going to get some ratio here that is either larger than, equal to, or less than 1. That tells you how the size changes. Then you're going to get either a negative or a positive sign, which will tell you that the image is inverted with respect to the object. If it's negative, it is upright with respect to the object if it's positive. I can also define this one other way. By looking at the relative heights of the image and the object, I can define this as the height of the image over the height of the object. Hi-ho if you want to, right? It's off to physics we go, I suppose. So the magnification here and the thin lens equation are the two workhorses to solve problems with this. Let's do this example with some numbers so that we can see what happens. And I should point out, notice the initial conditions here. My object is farther away from the lens than the focal length. So the focal length is going to be some number, the distance to the object will be some number less than that. So if I do this, let's say that for this system I find that the focal length is 10 centimeters. I find that my distance to the object is equal to 15 centimeters. And I'm going to ask, what is the distance to the image and what is the magnification of the image? All right, well, I just look over here on my other sheet, which I just moved, and to find the distance to the image, I just copy down that equation in its most useful form. Again, feel free to start. You should start with the full equation for about 3 or 4 times until you get used to getting to this form. But once you're there, you can just memorize it and go on about your business. But that is the thin lens equation, solved for the distance to the image. So I'm going to have to keep track of units. I'm going to have to keep track of any negative signs that come around. If I plug in numbers here, though, I've got 10 centimeters times 15 centimeters. Make sure I'm still in frame. Good. Divided by distance to the object, which is 15 centimeters, minus focal length, which is 10 centimeters. Out of that, I get 150 square centimeters in the numerator, 5 centimeters in the denominator. One of these units will cancel. It looks like I get 30 centimeters. So let's make sure that this at least somewhat matches up with what I've drawn. I don't expect what I've drawn to be insanely accurate because I drew it with a Sharpie and no straight edges, right? But I do expect it, at least qualitatively, to see some crosstalk between my geometry and my mathematics. I realize that geometry is mathematics. Don't write me emails. All right, so 30 centimeters is my distance to the image. That's larger than the distance to the object and the focal length, and it certainly looks like that is larger than that. So I feel good about that. Qualitatively, this matches up well. Let's do the magnification and see what that tells us. Magnification is going to be minus d to the image over d to the object. That is going to be minus 30 centimeters over distance to the object, which is 15 centimeters. I'm going to get out of that a minus 2. Okay, so the minus tells me that my image should be inverted. Check. And it tells me it should be twice as large. So I look at my drawing and go, that's definitely not twice as large. But can I reasonably justify going, okay, it probably doesn't look twice as large because I'm just not a good artist? And I can say, yeah, probably so. What you should really be concerned about is if you get something that's positive here, but you have an inverted image here. You probably go, I made a sign error somewhere. Or if you get something like 1,000 here, that's probably telling you that you did something wrong. But within a good approximation, I think that this matches up really well with the mathematics. So this, I should say, is a general case of what you find when you place an object farther away from a converging lens than the focal point. You find that it produces a magnified, inverted image on the other side of the lens. Now, one more thing we have to talk about. Let's ask ourselves, is there actually light propagating over here where the image is formed? And that might make it be strange to you until you've seen a case where that's not the case. But the answer is yes. These light rays are actually here. They actually pass through the lens and they actually propagate down here and they actually meet together and they form an image. Okay? If there are actually light rays propagating there where the image is formed, what we can say is that this image is real. A real image is produced by actual light rays actually in the space where the image is formed. The upshot of a real image is that it can be projected. And in point of fact, if you've ever been to a movie or are watching a PowerPoint presentation projected onto a screen, this is exactly what's happening. Over here on one side of the lens, this is probably a series of lenses, is a little bitty screen showing what you are watching. That light comes from the screen and passes through a lens and then passes out into space and is projected up onto a screen here, or actually probably over here. But the point is, this is how projectors work. So real images are formed by real light rays and they can be projected. Okay. In the next video, we're going to look at another case where I put the object somewhere different.